Now let's look at question number 2. Now question number 2 says a compressor operating at steady state takes in 1 kg per second of air at 1 bar and 25 degrees Celsius and compresses it to 8 bar and 160 degrees Celsius. Heat transfer from the compressor to its surroundings occurs at the rate of 100 kilowatts. Find out, the first part is, or part number A is, determine the power input in kilowatts, and the second part is evaluate the second law efficiency for the compressor. This means this is a question from the video on the second law efficiency illustrations, and in that we talked about a compressor and a pump. Alright, and we have to neglect the kinetic the kinetic energy and the potential energy changes. T naught and P naught, that's the dead state, 25 degrees Celsius and 1 bar. Now if you draw a compressor, let's draw the schematic first. So this is how a compressor would look like. Okay, so the entry of air is at a larger section, so this is the air which is entering section number 1, and it exits at a smaller section, so this is the exit, which is section number 2. Now there is some heat input, let us say. So the heat interaction, I would not say heat input, so let's have some heat interaction and work interaction of this control volume with its surroundings. Alright, now because it's a steady state operation, the steady flow energy equation for the compressor, okay, would be, so let's write that down. That will be equal to W dot is equal to Q dot plus M dot into H1 minus H2. So this is a steady flow energy equation of this compressor. Okay, now if you look at these values, I know the value of Q dot. The value of Q dot is 100 kilowatts. Now the direction of the flow of heat is from system to the surroundings, so it becomes a negative value. Alright, so it is minus 100 kilowatts, so this sign has to be in the opposite direction. This should be the value, or this should be the direction of flow, and the work should be the input in this case. Alright, next, the mass flow rate is 1 kilogram per second. Now we know the value of enthalpy is Cp into T. Alright, so H1 would be Cp into T1 and H2 would be Cp into T2. So the value of Cp, and because we are using air, so this data might not be given to you, so you need to remember this value of Cp for air. So Cp for air as the working fluid is 1.005 kilojoule per kg Kelvin. Alright, so T1 is 25 degrees Celsius. The entry is at 25 degrees Celsius, or you can say 298 kelvins. Alright, and T2, it is 160 degrees Celsius, which is 433 Kelvin. Alright, so if you find out this value of work input to the compressor, so W dot is equal to minus 100 plus 1 into 1.005, let's put it in a bracket, into, so let's not change it, there's no need to change the temperature into you can say the Kelvin values, because it will be a difference of these two temperatures, so it will pan out to be the same value. So T1 is 25 and T2 is 160. So when you calculate this in your scientific calcs, it would be a negative value, which will be around 236 kilowatts. So this is something that you should be getting after calculating. Alright, now After finding out W dot, why did we find out W dot? You'll just appreciate it in a moment, because for second law efficiency, I need to balance the exergy. So I need to have the exergy balance in place. So for exergy balance, if you write down the exergy balance for the compressor, it is equal to m dot into AF1 plus q dot into 1 minus T naught upon T, okay, minus W dot minus m dot into AF2 is equal to I dot. So I need to have a value for W dot, okay, to analyze this. Now let's take all the terms except W onto the right hand side. So we would have minus W dot is equal to m dot into AF2 minus AF1, so they will interchange in their signs, minus q dot into 1 minus T naught upon T plus I dot. So this is what you get. Now because it's a compressor, alright, so if you look at this, this is the exergy which is going in, alright, and this is the exergy that is coming out, and this is the destruction of the available energy. So the second law efficiency would become equal to m dot into AF2 minus AF1 divided by minus W or just W, okay, because it has to be a numerical value. So this becomes W dot. Alright, so I know the value of m dot, I know the value for W dot, I don't know the values for AF1 and AF2. So let's find these values. Now AF2 minus AF1, this is equal to H2 minus H1 minus T naught into S2 minus S1, and we need to ignore the kinetic energy changes and the potential energy changes. They can be taken to be zeros. Alright, so if you rewrite these values, so H2 is, we know it is CPT, so it becomes CPT2 minus T1. Let me write T1 again. Alright, now T naught is a constant. Okay, so what is the value of Cp? Now we are taking the compression of a gas, so it becomes Cp into natural log T2 by T1, okay, minus R into log P2 by P1. So this is the value of entropy change that you get. So this is this whole expression. Alright, now if you go further, you just have to plug in the values as it is. So it becomes 1.005 into 25, or not 25 but 160, I would say, yeah, 160 minus 25. Now T naught was 25, so it becomes 298. Cp again 1.005 natural log. Now this value has to be in Kelvin, so it becomes 433 upon 298 minus the value of R 0.287 into log 8. So this is the whole value. Now you can do the magic with your scientific calculators. So AF2 minus AF1 will become 201 kilojoule per kg. So this would be the value of AF2 minus AF1. Alright, so with this value I can easily find out the second law efficiency. and that was equal to the value of m dot into AF2 minus AF1 by W dot. So m dot is 1, this difference is 201, and the value of W dot is how much? If you look in, so this is 236, so this becomes 236, and upon finding out this ratio, it is approximately 85.3% as your second law efficiency. So this is how you have to find out this question on the second law efficiency. So I hope you understood this. So it was a straightforward application of the illustration of the second laws, where we analyze and find out the exergy balance and the second law efficiency for a compressor. So I hope you understood this and the whole topic on available energy, availability and irreversibility.